Hello there and welcome to the third part or the third module of 18 of the CCNA 200-120 exam fast track learning. This focuses, as you can see, on local area networks. Okay, so what are the objectives? Basically after going through this module, you should be able to describe the basic operation of Ethernet. Also, you'll be able to identify common Ethernet standards and their associated cabling and connectors. You should be able to describe the basic operation of wireless LANs, which is very popular these days, and also identify common wireless LAN standards. See, there are a number of LAN technologies in use at present. The most widespread are Ethernet, or CSMA/CD, which stands for Carrier Sense Multiple Access with Collision Detection. And there's also wireless LAN implementations. Other technologies include token ring, most frequently found in IBM sites, and FDDI, which stands for Fiber Distributed Data Interface. These are often used as the backbone of a LAN, but whose role in this respect has been increasingly taken over by some of the faster Ethernet technologies described later in this section. Modern LAN technologies have data transfer rates of up to 100 megabits or greater. So first of all, what we'll talk about is Ethernet. Originally Ethernet provided for 10 megabit communications over coaxial cables. This is now rarely seen in today's day. The most widespread current forms of Ethernet are unshielded twisted pair, or UTP cabling, to connect end stations to hubs or switches and operate at speeds of between 10 megabits and 1 gigabit. Hubs and switches can be interconnected to form larger LANs, often using faster Ethernet connections with speeds of up to 10 gigabits. Some of these faster Ethernet technologies use fibre-optic cabling. Early Ethernet implementations consisted of a number of network stations attached to a coaxial cable by network adapters, each one of which functioned as a radio frequency transmitter or receiver, as you can see in the screen. When a station sends a frame to another station, it includes the destination MAC address in the frame header. Every station reads this address. Only the station with a destination address reads the rest of the frame. Each end of the cable is terminated by a 50 ohm resistor in order to prevent signals from being reflected back from the end of the cable and corrupting data. In late implementations, the role of the cable is taken up by a hub or a switch. Ethernet uses a technique called Carrier Sense Multiple Access / Collision Detection, or CSMA/CD, to handle contention, which arises when two or more stations need to access the communication channel. In this case, we're talking about the cable, and this occurs when it's trying to access the communication channel at the same time. So before sending a frame, a station listens to the channel to see if it's already in use. If it is, the station wishing to transmit will wait. If the channel is not in use, the station will then transmit. It can happen that two stations that detect no traffic on the channel both start to transmit. In this case, the signals will overlap and the frames will subsequently be corrupted, and this is what's known as a collision. Each station can detect overlapping signals because the voltage on the cable increases. When a station detects a collision, it broadcasts a jamming signal to ensure that any other station also sending a frame gets to detect the collision, as you can see on the screen. The jamming signal achieves two things. Firstly, it allows the original sending station, shown as A in the picture to detect that a collision has occurred. In order for this to happen, A must still be transmitting when the jamming signal arrives. That is why there is a minimum Ethernet frame size of 64 bytes. The other function of the jamming signal is to ensure that the frame being sent is detected as being corrupt by any other stations on the cable, and so will be discarded. The jamming signal is a series of 48 alternating bits, zeros and ones, which will cause a CRC checksum calculation to fail. After their jamming signals have been sent, each station waits for a random back-off period before attempting to retransmit its frame. If multiple collisions are detected, the back-off period increases but still contains an element of randomness, which makes it less likely that the stations will try to retransmit again at the same time. As you'll see later in this module, modern switched Ethernet networks can eliminate collisions and so would not seem to require collision detection. However, the need for backward compatibility, for example hubs in networks, means that CSMA/CD is still supported and included in specifications of Ethernet. So let's look at the format of an Ethernet frame. Okay, the format of an IEEE 802.3 frame is shown on screen at the moment. Okay, so what you've got reading from the left, you've got the frame check sequence on the left, then you have the data, effectively. The first 3 bytes contain the source SAP and destination SAP, and control fields, each one a byte long. You've then got the length, which is the length of the data field in bytes, followed by the source address or source MAC address and destination MAC address. So because the IEEE 802.3 frame has a length field rather than a type field, some bytes from the beginning of the data field are used to specify the type of data being carried. These are the source SAP and destination SAP fields, and they are usually set to the same value. The control field can be used to specify other types of service, such as a connection-oriented service where frames are acknowledged once that they have been received successfully. So we're talking about TCP here. Most Ethernet implementations provide a connection-less service which does not use acknowledgements, so in other words a UDP. If a frame is found to be corrupt, because the CRC calculated by the receiver does not match the one at the other end of the frame, then the frame is simply discarded. The SAP and control fields are defined by the IEEE 802.2 Logical Link Control, or LLC standard. Because of the extra overhead involved in processing the LLC information in IEEE 802.3 frames, Ethernet 2 frames are more widely used, especially for carrying IPv4 packets. Another reason for this is that IEEE 802.2 does not support IPv4 properly, and yet another layer of header information called SNAP, or Subnetwork Access Protocol, needs to be added to provide IPv4 support. Although the Ethernet 2 frame does not have a length field, this does not cause a problem for IPv4 packets carried inside Ethernet 2 frames, as the length of the packet is specified in the IP header. Fortunately, modern Ethernet implementations can detect which type of frame is being used by making use of the fact that the maximum value of the length field in an IEEE 802.3 frame is 1500. The values of the corresponding type field in an Ethernet 2 frame are all greater than or equal to 1536. Let's move on. So there are now a number of different Ethernet implementations using a variety of cables and connectors. So we're going to start by looking at coaxial Ethernet cabling and then moving on to describe UTP, or unshielded twisted pair, and fibre optic cabling. So coaxial cabling consists of a central conducting core surrounded by a dielectric insulating layer such as PVC or Teflon, which is in turn surrounded by a mesh of copper or aluminium. This shields the core from stray electromagnetic radiation, which might induce voltages in the core, corrupting the data signals. The central core carries electrical signals as voltages relative to the outer mesh, which should be earthed. The outer plastic shield protects the mesh. There were two types of coaxial cabling used for early implementations of Ethernet, referred to as thicknet and thinnet. Thinnet is flexible and looks much like TV aerial cable, but thinner, approximately 0.5 centimeters in diameter. Thicknet is less flexible and about 1 centimeter in diameter. Thicknet offers better protection against electrical interference and so supports longer run lengths of cable. Both types of cable support data transfer rate of up to 10 megabits per second and have an impedance of 50 ohms at the operating frequency of 20 megahertz. Thinnet cabling is attached to a network adapter using BNC, or British Naval Connector, or even Bayonet Network Connector technology. Basically what you see on the screen now, you can see a Thinnet cable attached to a BNC T-piece on the left, and there is a 50 ohm terminator on the other side of the T-piece. The network adapter shown is a combination card with a BNC connector for Thinnet cabling and an RJ45 connector, which could be used instead for a connection to a hub via a UTP cable. The maximum run length of Thinnet cabling, i.e. without the use of any repeaters, is 185 meters. On the right hand side we've got we're showing thicknet cabling, which is less flexible and harder to install, but it has a run length of 500 meters. So in comparison to Thinnet, it's 3 times as long. It uses a separate transceiver to put a signal onto the cable. This is fixed onto the cable using a vampire tap, as you can see. Which is a metal spike, and this pierces the outer layer of the cable to connect the core. Transceivers can only be attached to the cable at intervals of 0.5 meters, which are marked on the cable itself. Connection to the computer's network adapter is via a drop cable of maximum length of 50 meters. This connects to the attachment unit interface, as you can see at the bottom picture of the network card. This port uses a DB15 connector. Thicknet was used to provide the cabling backbone in computer sites, a role now taken by fibre-optic cable or fast Ethernet cabling. Cisco routers and switches have never supported Thinnet. Some older Cisco devices had Thicknet interfaces. In order to connect these devices to Thinnet cabling, you needed a special transceiver with 2 connectors. One connected directly to the AUI interface, and the other was a BNC connector connecting directly to the Thinnet cable. In addition to Thinnet cabling using BNC connectors, coaxial cabling is also used in video and TV, as well as cable modem systems. So on the screen, as you can see, on the left, a standard Bell & Lee TV aerial connector, and on the right is an F-type connector used in modern cable systems, including cable modem networks. The cables themselves are specified according to the number of RG, or radio guide standards, some of which are shown on the next slide. Okay, so I suggest you pause that if you want to memorize those. This is more of information for you, really, starting from the ground up. This won't be covered in the exam itself, but it's handy to know. It is legacy information, but yeah, knowledge is power. So let's move on. Sorry. Most modern Ethernet implementations use twisted pair cabling to connect end stations to hubs or switches. On the screen now is a typical example of a hub, Ethernet hub. A twisted pair cable consists of up to 8 insulated wires, which are arranged in pairs twisted together, like so. Each pair forms a part of a communication circuit. Any electrical current flowing down one wire of the pair will return via the other. The wires are twisted together to minimize the effects of electromagnetic interference. The effect of any current induced in one wire of the pair will be cancelled out by that induced in the other, as long as the wires are close together. One of the main sources of interference in a twisted pair cable is neighbouring wire pairs, which can radiate away some of the energy from their signals, and this form of interference is called crosstalk. Twisted pair cable, which consists of 4 wire pairs enclosed within a protective plastic covering, is called an unshielded twisted pair, or UTP. In environments with lots of electromagnetic noise, for example from heavy electrical machinery, you might need to use shielded twisted pair, or STP. In STP, each wire pair is enclosed within a metallic foil to shield the wires from interference. Sorry, I've gone one too far, I do apologise. The entire cable is also shielded. STP cabling provides better protection against interference, but is more expensive than UTP, which is the usual choice for most networking environments. So twisted pair cabling typically uses an RJ45 connector, which is the screen I went to there. And RJ stands for registered jack. More formally, they are known as 8P8C connectors, though the term RJ45 is widely used. So when making a cable, it is important to connect the correct wires to the correct pins on the RJ45 connectors. To help with this, the wires in a UTP cable are colour-coded. Each pair of wires has one wire with a solid colour and the other white with a stripe of the same colour through it. As you can see, you've got blue, solid blue and blue stripe, orange, orange stripe, and so on. So holding the cable so that the end points to the right, as shown in the diagram, and the metal contacts of the RJ connection or RJ connector are facing you, the pins are numbered sequentially from pin 1 at the top to pin 8 at the bottom. So straight through, the different types of cables I'm going to go through now. So starting with straight through cables. UTP Ethernet cables are most often used to connect end stations to hubs or switches. Most implementations of Ethernet only use 2 of the wire pairs. Pair 2, connected to pins 1 and 2, forms part of the circuit used to send data from end station to the hub or switch. Let's have a look. Pair 3, connected to pins 3 and 6, form part of the circuit used by the end station to receive data from the hub or switch. This arrangement is known as straight through cable, hence the name. Its pin mappings, or pinouts, are shown on screen. The other pairs are not used. One of the advantages of using UTP cabling is that it can support full duplex transmission. Separate send and receive circuits allow both sides to transmit simultaneously. The interface of the end station is also known as an MDI, or medium dependent interface. And the interface of the switch or hub shown on screen is known as an MDIX, or medium dependent interface crossover, because the transmit pins on the end station have been connected to the receive pins on the switch or hub, and vice versa. So let's move on to crossover cables. Sometimes it's convenient to connect 2 end stations together directly, for example to transfer files between computers not connected to a LAN. A straight-through cable cannot be used for this, as each device would be transmitting on the same circuit. In this case, you need to use a UTP cable wired differently. The transmit pins of each end station are connected to the receive pins of the other. This arrangement is known as a crossover cable, as you can see on the screen. The pinouts, 1 going to 3, 2 going to 6, and vice versa. Crossover cables are also used to connect hubs and switches to other hubs and switches to form larger LANs. Some hubs have a special port which is used for connections to other hubs or switches. This has the crossover built into the port so that ordinary straight through cable can be used. Sometimes this port can be activated by a button, allowing you to select whether it is used as a straight through or a crossover port. Modern switches such as 2960 series are able to detect which pairs are being used by the other device's circuits and configure their ports as MDI or MDIX accordingly. This avoids the need to have two different types of cable. This automatic detection feature is called Auto MDIX. So there are two standards for assigning wires to pins in a straight through UTP cable. These are specified by the EIA and TIA, or Electronic Industries Alliance / Telecommunications Industry Association. Either standard may be used, and I've got the table up on the screen at the moment. The EIA/TIA 568 standards also specify the categories of UTP cable. The higher categories are capable of supporting faster data transfers. So on the screen now, I'll show the different speeds, the category on the left and obviously the speed supported on the right. One of the ways that they can do this is by specifying more twists per meter for the wire pairs. Categories 1, 2, 4 and 5 are no longer recognised by EIA or /TIA. Run lengths have only been shown for recognised cables. Cables are 2 pair unless otherwise stated. There is also a Cat 7 standard from IEC, stands for International Electrotechnical Association, and this specifies an enhanced STP cable supporting speeds of up to 10 gigabits per second. I'll just quickly explain loopback adapters as well. Hardware loopback adapters are used in networking testing to redirect signals from the output circuit of a port to its input circuit. In this case of Ethernet over UTP cabling, the loopback adapter connects pin 1 to pin 3 and pins 2 to pin 6. So let's just move on to fibre optic. So nowadays fast connections between Ethernet switches are often made using fibre optic cabling, which consists of a centre glass core surrounded by cladding also made of glass, which is surrounded by protective plastic coating, as you can see on the screen. Some cables have a plastic core and cladding, but these have a greater attenuation, i.e. the light signal weakens more quickly. The materials of the core and the cladding are made in such a way that the speed of light through the core is less than through the cladding. In this case, if a beam of light enters the core and strikes the boundary between the core and the cladding at a small enough angle, the light is totally internally reflected, remaining trapped in the core, as shown on the screen. Signals are transmitted by modulating a light source, such as an LED, at one end of the core and detecting it at the other end. Laser LEDs can be used to achieve longer ranges. The wavelengths of light used are in the infrared area of the spectrum, typically between wavelengths between 850 nanometers and 1550 nanometers. The diameter of the fibre is usually between 9 and 62.5 microns. Transmission usually takes place in one direction, so fibre optic cables generally come in pairs. Data transmission rates are high, typically 1 gigabit per second and higher. So modal dispersion. If shorter wavelengths of light are used with fibres of larger diameter, it is possible for light to travel through the core by more than one path. This is known as multimode transmission. This means that the leading edge of a pulse of light will gradually spread out as it travels down the fibre, a process known as modal dispersion. Eventually, the leading edge of one pulse will catch up with the trailing edge of a previous pulse, causing the signal to become corrupt. As a result, fibre optic cables which allow multimode transmission must be short enough to prevent this form of signal corruption. Multimode fibre is typically 50 or 62.5 microns in diameter. It is usually used with 850 nanometers light from diodes. Because it's subject to modal dispersion, run lengths are restricted to hundreds of meters. Single mode fibre, or SMF, with smaller diameters such as 9 microns, for use with longer wavelight between 1310 or 1550 nanometers, are known as single mode fibres because the light can only take one path through the core of the fibre. As there is no modal dispersion, longer run lengths of cable can be achieved, particularly when the light source is a powerful laser. Run lengths of 10 kilometers can be achieved. However, SMF cable is more expensive than MMF cable. So let's move on to the fibre optic connectors. Fibre optic links use a pair of fibre optic cables. Some of the main types of connectors are shown on the screen. Each cable attaches to the network adapter through a fibre optic connector. The ferrule connector, or FC, is widely used in storage area networks, or SANs, which allows servers to talk to disk arrays using fibre optic cable. The straight tip, or ST, connector uses a BNC interface. Both the subscriber connector, or SC, and the lucent connector, LC, interfaces have latches which hold the connector firmly in place. The LC is effectively a smaller version of the SC. The mechanical transfer registered jack, or MT-RJ, as you see in the middle, connector is a small form factor connector which takes a single cable holding two fibres. Note that the connectors are used with twisted pair of cables, one to transmit and the other to receive. Now, it's not necessary to have the same type of connector at both ends of the cable. As the first connections are optical, it is important that the intensity of the light signals is not attenuated at the connection. For this reason, fibre optic connectors often have dust covers to prevent the accumulation of dust on the optical surfaces of the connectors when they are not in use. Sorry about that. Fibre optic converters. Each fibre optic cable attaches to a network adapter, one which you can see on the screen, which has one or more sockets, each which contain a small transceiver. This transceiver converts light signals arriving on the cable to electrical signals and vice versa. Early examples of these transceivers were known as gigabit interface converters, or GBICs. These have been superseded by even smaller devices called small form factor pluggable, or SFP transceivers. On the screen is an example of a network adapter with some SFP transceivers. The adapter has 4 sockets. The 2 transceivers on the left have been fully inserted. The other 2 have been partly extracted. Another 2 transceivers are shown by the side of the adapter, as you can see below, with their black dust covers in place. The benefit of having swappable transceivers is that network adapter can be bought without having to commit to a particular type of fibre optic cable or connector. Appropriate transceivers can be added or replaced as needed. So, talking about safety, the plenum is the space between false ceilings and the floor above. Standard PVC-based cabling gives off poisonous fumes when it burns. Any fumes in the plenum could very easily spread quickly to other parts of the building. For this reason, cabling which is to be installed above ceilings or above false ceilings or under floor should be of plenum grade. There is a separate, even more stringent riser grade standard for cables used in ducting. We've already seen that thicknet and thinnet coaxial cables were the basis of the earliest implementations of Ethernet. Thinnet was replaced as a means of connecting end stations to the LAN by the use of FTP drop cables to connect the stations to hubs and switches. The earliest form of Ethernet using UTP offered data transfer speeds of 10 megabits per second using a drop cable up to 100 meters long. So I'll put on the screen early Ethernet implementations. As you can see, you've got thick wire Ethernet, which is 10 base 5, and the naming convention has three parts. So you've got 10, which is the speed, you've got the channel, base, and medium 5. The speed specifies the data rate in megabits per second. The channel, i.e. base, is for baseband, or it could be broad for broadband, and the medium specifies the physical medium or the cable used. Baseband transmission uses all the available bandwidth for a single channel, whereas broadband transmission divides the available bandwidth amongst a number of channels. Most of the Ethernet implementations that we shall consider use baseband transmission. In the case of coaxial cables, the medium type is designated by the maximum run length of a cable in hundreds of meters to the nearest hundredth. So thicknet is known as 10 base 5 because its speed is 10 megabits. It's using baseband transmission and over a cable with a maximum run length of 500 meters. Thinnet is known as 10 base 2 because it has a maximum run length of 185 meters, approximately 200 meters. In the case of 10 base T, the medium type is designated as T for twisted pair. This has a maximum segment length of 100 meters from station to hub or hub to hub and supports up to 1024 stations. The later implementations of Ethernet, which we are about to cover, use extensions of the same naming scheme. The original Ethernet standards, which supported speeds of up to 10 megabits per second, have been superseded by fast implementations. The typical speed of current installations is 100 megabits per second, or fast Ethernet. A number of IEEE 802.3 standards have been developed to support fast Ethernet speeds over copper and fibre. Connections to the desktop are almost always by copper at speeds of up to 1 gigabits per second. Fibre is often used for connecting infrastructure devices such as switches and routers. These connections can support speeds of up to 10 gigabits per second. Copper cabling can also be used to interconnect infrastructure devices. 100 megabit per second Ethernet is specified by IEEE 802.3U and can be run over 2-strand fibre, 100 base FX or 2-pair Cat5 UTP cable, 100 base TX as shown on the screen. They are known collectively as 100 base X in reference to the fact that the use of two physical channels was developed from the ANSI standard X3T9.5 used to define fibre distributed data interface, which is described later in this module. There was another standard 100 base T4 which used 4-pair Cat3 cable or better. This was designed to allow for faster speeds without the need to upgrade the cabling. It was never widely used as most sites upgraded their cabling. The 100 meter run length for 100 base TX allows it to replace 100 base T with minimal disruption. Note that the term 100 base TF is sometimes used for 100 megabits per second Ethernet running over fibre. However, there is no such standard. Gigabit Ethernet, or 1000 megabits per second Ethernet, is supported over the media types shown on the screen. 1000 base T is IEEE 8023AB standard and supports 1 gigabits per second Ethernet to the desktop via 4-pair Cat5 or better TP cable. It has the same run length as 100 base TX and 10 base T, making for easier upgrades. 1000 based CX or copper follows the standard 802.3Z and also supports 1 gigabits per second Ethernet over copper between network infrastructure devices. 1000 base CX specifies either 150 ohm coaxial cable or STP with a maximum run length of 25 meters. The remaining 802.3Z specifications all use fibre. So you've got the shortwave fibre, which is SX, 1000 base SX. This uses shortwave infrared in multimode fibre-optic cabling with run lengths of up to 500 meters. 1000 base LX or long wave fibre. This uses long wavelength infrared in multimode or single mode fibre optic cabling. SMF supports run lengths of up to 5 kilometers. Finally, you've got 1000 base LH, which stands for long haul fibre. This uses long wavelength infrared radiation in single mode fibre optic cabling, but uses improvements in the detection equipment to achieve run lengths of up to 10 kilometers. 10 gigabits Ethernet is defined by 802.3AE. It is used for interconnecting infrastructure devices primarily. There are 3 main cabling specifications: SR standing for shortwave, LR for long wave, and ER for extra long wave. They are shown together on the screen with their maximum run lengths. There are variants of these implementations called 10G base SW, 10G base LW, and 10G base EW respectively. They have the same cabling types and run lengths as their counterparts as on the screen, but the difference are with the physical interfaces and insofar as they're designed to interoperate with optical WAN networks using the SONET standard. SONET stands for Synchronous Optical Network. We'll cover SONET in more detail in Module 4, which is about wide area networks. So we're going to move now on to LAN switching. Now that we've seen some of the basics of Ethernet and the way that Ethernet LANs are cabled, we can look at in some more detail at the role switches play in modern LAN environments. In fact, switches are crucial to most LANs other than the smallest home office networks. To understand why this is, we need to look at the situation before the use of switches became widespread, when LANs were simply connected through hubs. So, a hub connects together a number of stations, as you can see on the screen, using a single shared channel. There are 2 important consequences of this. First, only half duplex transmission is possible. Secondly, each station contends with others for access to the channel. So if 2 stations start to send a frame at the same time, there will be a collision. This is even true when hubs are linked together to form a physical tree topology shown in this slide here. There is still a single channel shared by all stations on the LAN. When connecting 2 hubs together, you need to use a crossover Ethernet cable unless your hub has a special port which has the crossing of the transmit and receive wire pairs implemented in the port itself. So that if it has, then you can use an ordinary straight through Ethernet cable. The port will usually be marked as an uplink port. Some uplink ports have an associated button which can be used to turn the uplink functionality on and off, so that the port can be used to connect to an end station using a straight-through cable if required. As we've seen, switches function as multi-port bridges. There is not the same degree of contention because there is no longer a single channel. In addition, if each port is attached to only one station, full duplex transmission is possible. Remember that most UTP Ethernet cable uses two wire pairs, one to transmit and one to receive. If two stations simultaneously send a frame to a third station, no collision occurs because the switch is able to buffer frames. However, it is possible for a port on a switch to be connected via crossover Ethernet cable to a port on a hub, as shown on the screen. In this case, only half duplex transmission is possible on the cable between the switch and the hub, as the hub only supports half duplex transmission. One way of describing these different contention mechanisms is through the concept of broadcast and collision domains. A broadcast domain is a collection of computers, routers, end stations, which can receive broadcast frames from each other. All the networks that we have just seen are examples of a single broadcast domain. Is a collection of nodes where a frame sent by one node can collide with a frame sent by another. You can connect a LAN connected only through hubs is an example of a single collision domain, as shown on the screen. Forward broadcast packets. It also comprises a single broadcast domain, also shown. If each port of a switch is connected to a single node with full duplex transmission, as shown on this screen here, then each node is in its own collision domain, as it can send and receive simultaneously. In other words, there are as many collision domains as there are active ports on the switch. Very important. This is very important for the exam. The node also comprises of a single broadcast domain. If a port on a switch is connected to one on a hub, the port on the switch needs to be configured to operate in half duplex mode, and all the nodes attached to the hub will also be in the same collision domain, as shown here. Again, the nodes also comprise of a single broadcast domain. Modern switches can auto-detect the presence of a half-duplex device and configure themselves accordingly. On the screen here you can see how a router has been used to create more than one broadcast domain. Note that each switch has 4 active ports, including the port attached to the router. If each port is configured for full duplex transmission, which is the default mode, then there are a total of 8 collision domains. Most switches do not require any configuration in order for them to function as basic switches. They just work out of the box. You plug them in, turn them on, and they will work. A typical default configuration, I'll show you in a couple of slides, but I'll show you that's what's an example of a Cisco switch. It's a 2960 series switch, and this particular model has 48 fast Ethernet ports capable of operating at 100 megabits or 10 megabits, and 2 gigabit Ethernet ports capable of operating at 1000, 100 or 10 megabits on the right hand side here. Each port has a number and a diagnostic LED associated with it. So on the left hand side of the panel, this is a blown up image of the left hand side of a Cisco switch. There are a number of diagnostic LEDs and a port mode selector button. The mode selector button is used to select what information is displayed by the port LEDs. The 2 upper diagnostic LEDs are the system LED labelled SysT and the redundant power system LED labelled RPS. you can see a description of the system LED output on the right hand side. The redundant power system is a Cisco device that can provide backup power to one of up to 6 switches in the event that its power supply unit fails. Note that an RPS is not a UPS, or an uninterruptible power supply. It does not provide any backup for mains power. What it is, it provides DC power direct to the switch's system board in the event that the switch's power supply unit fails. It can only provide power to one of the connected switches at any time. And you can see a description of the RPS LED output on the next slide, which is here on the screen at the moment. So next I'm going to explain about port display modes. Okay, so on the screen at the moment are the 3 port display modes: STAT, DPULX and speed. Self-explanatory. The first one is port status, then we've got the duplex mode, and then followed by the port speed. Whenever there is a mode button, a port mode selector button just below the port display mode LEDs, and by pressing the button you can cycle through the modes one at a time. The default mode is STAT, and whenever you change this to another mode, the mode will return to STAT after 30 seconds. So I've just got a few slides just showing what the status of the lights would mean when you change the status itself. So let's go to, so when in STAT mode, so you've got solid green, flashing green and solid amber, and you've got the different states. Solid amber port is in not forwarding. That would relate to spanning tree protocol, where a port can be put into the blocking state, and that runs on all switches. We will cover more about STP later on in the course. Then you've got the duplex and speed modes. Okay, so off meaning half duplex, green meaning full duplex, and the popular one is when you're in speed mode, port operating at 10 megabits per second, or green operating at 100 megabits per second. So moving on to the rear of the router, you've got the DC power in. This is a socket for the mains electricity power. There is no power switch as such. There is an outlet for a cooling fan near the centre of the panel. Obviously take care not to obstruct this, so that otherwise it will get very hot. On the rear panel you can also see a 14 pin connector for the backup DC power output from RPS, explained below, and that's what you see on the screen at the moment. That's for the RPS. The only other item of interest on the rear panel would be the console port, excuse me, and that's obviously labelled console. The console port is used to manage the router from a directly connected terminal, usually from a PC running a terminal emulation software such as HyperTerminal or PuTTY or Secure CRT. The console port uses an RJ45 connector, as you can see, attached to a proprietary Cisco rollover cable, which is usually a flat cable with 8 leads, and it is terminated by RJ45 connectors at either end. It is known as a rollover cable because of the way the pins at each end are connected to each other, as you can see it in the next slide here. I do apologise. There. As you can see, 1 goes to 8, 2 goes to 7, 3 goes to 6, and so on. Console cables provided by Cisco equipment are usually pale blue, the infamous pale blue colour. They're flat, as shown in the next screen, like so. However, twisted pair cabling is not necessary, as the data rates are very low, usually a few kilobits per second, and so crosstalk is not a problem. The console cable would connect to a terminal used to manage the switch directly to the console port. The console cable is connected to a serial port on the terminal, usually a PC, through an RJ45 to DB9 converter, as shown here. Or you could do an RJ45 to a USB converter if your PC hasn't got a serial port. There are USB to serial converters. So that covers the Cisco switch. We're going to now move on to VLANs. So a switch can effectively be partitioned into separate broadcast domains by defining virtual LANs or VLANs, and then assigning ports to those VLANs. This can help reduce broadcast traffic, especially in large networks. So the diagram there shows a switch that's split into 3 different VLANs, namely red, blue, green. Usually in the working environment it might be the finance department, HR department, sales department. So by default all ports are assigned to VLAN 1. If you want to partition your switch, first you need to have to configure more VLANs on it. Once you've created your VLANs, you can then assign ports to a VLAN. A port can only be assigned to one VLAN at a time. A port can be assigned statically to a VLAN. Alternatively, it is possible to set up a server to assign ports to VLANs dynamically based on some property of the device attached to the port, such as its MAC address. That would be the obvious one. So on the screen you'll see that PC1 and PC2 are in different VLANs. So 1 being in red, 2 being in blue VLAN. So they cannot communicate with each other unless a router is used to connect the red VLAN to the blue VLAN. Each VLAN runs its own instance of the spanning tree protocol, and we will cover more about VLANs in module 16, labelled configuring VLANs. Okay, so now I'm going to move on to explaining VLAN trunking. So the ability to create VLANs would be of limited use if VLANs could not span multiple switches in a network, for example. Let's just go to the next slide. So here you'll see 2 switches connected together. The same 3 VLANs, red, blue and green, have been defined on each switch, and ports on each of the switches have been assigned to each of the VLANs. PC1 in the red VLAN, down here on the left, on the lower switch, can send frames to PC2 in the red VLAN on the upper switch without the need of a router. The ports attached to the end stations are access ports. However, it is possible to configure a port as a trunk port. Trunk ports are used to connect switches together to pass VLAN traffic from one switch to another. In order to do this, earlier Cisco switches used a Cisco proprietary ISL, meaning Inter-Switch Link protocol, while a Cisco 2960 switch uses the IEEE 8021Q protocol, which is an open standard. These 2 protocols are incompatible, so the 2 types of switch cannot be connected directly via trunk ports. The ISL protocol also suffers from a serious drawback. By adding a tag to the original Ethernet frame, it might create a frame exceeding the maximum Ethernet frame size. This is not a problem for Cisco switches running ISL, but it could cause frames to be rejected by other switches. The IEEE 8021Q protocol, however, was developed to avoid the problem of exceeding the maximum Ethernet frame size and allow interoperability between switches from different manufacturers, basically. In this case, the size of the original frame is not altered. The VLAN information is added to the existing fields in the frame header and then removed by the receiving switch. The protocol also recalculates the CRC to match the changed frame contents. As we have seen, each VLAN defines a broadcast domain, running its own instance of the spanning tree protocol. So looking at the diagram on the screen, you should be able to see that there are effectively 3 broadcast domains. The number of collision domains will be equal to the total number of active access ports. If routers are used to interconnect the VLANs, the number of broadcast domains does not change, as routers do not, by default, forward broadcasts. So now we're going to move on to PoE. So far, we have given routers, PCs, hubs and other switches as examples of the kinds of devices that are connected to switches. All of these come with their own power supplies, with the exception of small passive hubs which do not require power. Nowadays, the LAN infrastructure is being used more and more to deliver telephony to the desktop through VoIP, or Voice over IP, using IP phones that are connected to switches by UTP Ethernet cables. A conventional telephone derives electrical power that it needs from the telecommunication provider's telephone network. In the case of IP telephony, this power is provided through the Ethernet cable using a technique called Power over Ethernet, or PoE. Most variants of Ethernet that use UTP cable only make use of 2 of the 4 wire pairs in order to carry data. This leaves the other wire pairs available to deliver power. Some of the switches are PoE enabled and can deliver power directly through their ports. If you need to support IP phones but your switches do not provide PoE, an alternative solution is to use power injectors, as you can see on the right hand side on the diagram. These take data from a UTP cable attached to a port on the switch and electrical power from the main supply, and pass data and power to the IP phone via another UTP cable. So we move on to WLANs. Wireless Ethernet. The basis of today's wireless LANs is an extension to the Ethernet protocol pioneered by the Wi-Fi Alliance, an industry association devoted to promoting the growth of wireless local area networks. Although they are based on the Ethernet protocol, WLANs use specific radio frequencies rather than copper or fibre optic cables to transmit data. This has a number of consequences which account for some of the differences between Ethernet and WLAN protocols. Let's have a look. So security. Any PC equipped with an appropriate wireless adapter can access the radio frequencies used by WLANs. Consequently, authentication and data encryption have become important features of WLAN standards. Duplex transmission. In modern LANs using switches, full duplex transmission is possible between the switch and any PC directly attached to it. If 2 WLAN devices transmit at the same time, using the same frequency, the signal will be garbled. There are no separate transmit and receive circuits except in the IEEE 802.11n standard. To avoid this, most WLANs need to use half duplex transmission. Range. Because most of the radio frequencies currently used by WLANs are unlicensed, they can be used by other devices such as cordless phones as well as by other WLANs. In order to prevent too much interference between competing systems, the power of the radio signals is limited. This means that the range of WLANs is usually limited to a few tens of meters. And finally, collision handling. The CSMA/CD algorithm used by Ethernet depends on each station being able to detect a collision. For this to work, stations need to be able to listen to the channel while transmitting. Most current wireless adapters cannot do this, so WLANs use a collision avoidance mechanism, CSMA/CA, which introduces delays between transmissions to minimize collisions. Radio transmission uses a radio wave with a base frequency. This wave is modulated to carry information. Modulation involves changing some characteristic of the wave in order to encode data. You have already seen examples of modulation techniques in Module 1, which was Introduction to Networks and Data Communications. They include amplitude modulation, frequency modulation, and phase modulation. Modern radio frequency data encoding techniques, such as those used by WLANs, usually include more sophisticated combinations of these basic types of modulation. The use of radio frequencies is governed by international and national regulatory authorities, such as Ofcom in the UK and the FCC in the US. These authorities determine which frequency ranges or bands can be used and for what purpose. Some frequency bands are licensed, and usually for a fee, to particular users, such as radio stations. Others, like most current WLAN frequency bands, are unlicensed, i.e. free for anyone to use, subject to certain restrictions, such as on the power of the transmitted signals. One of the disadvantages of using unlicensed channels is the possibility of interference from other devices. For example, many cordless phones use the same frequency bands as WLANs, and microwave ovens also radiate energy at these frequencies. Let's have a look at the bands here. I'll show you. Now, the bands authorised for WLAN transmissions are in the UK, are shown on the table on the screen at the moment. All of these are unlicensed. Note, the frequency range of the 2.4 GHz band in the UK is slightly different from the US values given in table on the screen. This is also the case for the 5 GHz bands. There are also differences between power limits set by the authorities. For these reasons, you should not operate WLAN equipment designed for the US in the UK and vice versa. In WLANs, interference from other radio frequency sources can cause loss of data, and this is very commonplace in serviced offices, for example, where there are multiple businesses all running their own wireless network, and so therefore interference is commonplace. Frames which are corrupted due to interference need to be retransmitted, and this reduces the overall speed of transmission. To minimise the effect of interference, WLAN technologies spread their transmission over a number of different frequencies in such a way as to reduce the chances of two different systems using the same frequency at the same time. Now, there are a number of techniques used to achieve this. You have FHSS, DSSS, OFDM and MIMO, and they are described in the following sections. So, frequency hopping spread spectrum. The sending and receiving stations switch between frequency according to an agreed sequence. If another WLAN is using the same frequency range, the chances of both WLANs using the same frequency within that range at the same time are minimised. As you can see on the screen, the effect of two WLANs using 5 different frequencies over a number of time slots. In this example, interference only occurs in slots 6 and 9. When the data originally sent in these time slots is retransmitted, it is likely to be sent without interference. If there is interference from another source, say a microwave oven, at a particular frequency, then only the data transmitted at that frequency will be affected. And it is likely that when that data is retransmitted, it will be sent at a different frequency. Rather than hopping from one frequency to another, DSSS, or Direct Sequence Spread Spectrum, mixes the data signal with a large amount of redundant information and transmits it over a number of different frequencies simultaneously. The redundant information is subtracted by the receiver to recover the original signal. The redundant information, sometimes known as the chipping code, is designed to be like white noise, random signals of equal strength over an entire frequency channel. Because there is much more redundant information than actual signal, the entire transmission appears to be random noise, making it much harder to detect as meaningful signal. This means that it is harder to intercept communications, and it's for this reason DSSS has been used in military communications. Some of the extra information also acts as a checksum on the original signal, allowing it to be reconstructed if some of it is damaged by interference from other sources. When using DSSS in the 2.4 GHz band, each WLAN does not spread its signals over the entire 82 MHz frequency range of the band. Instead, the band is divided into 14 channels, each with a bandwidth of 22 MHz, shown on the screen. There are regional differences between the number of channels available for public use. For example, in Japan, all 14 channels can be used. In Europe, you're allowed 13 channels, whilst in the US only 11 are available. By using different channels for two WLANs in the same vicinity, you can reduce the potential for interference. So on the screen you can see the channels overlap. In fact, the centre of each channel, where the signal is strongest, is only separated by 5 MHz from its nearest neighbour. As a result, there are only 3 non-overlapping channels. In the US, there are channels 1, 6 and 11. And in the other regions, there are other possible combinations, such as 2, 7 and 13. But there is still fundamentally a limit of 3. When operating separate channels in the same vicinity, you should choose them to be non-overlapping if you can. It is possible to use overlapping channels, but there will be more interference the closer the channels are to each other. This will result in increased retransmissions of frames because they've been corrupted, and then therefore leading to decreased data transmission speeds. So moving on to OFDM, which is orthogonal frequency division multiplexing. So like DSSS, this technique spreads the signal over several frequencies simultaneously. One of the problems with using different frequencies which are close together is crosstalk, where there is interference between signals on neighbouring frequencies, as you see on the screen. This is because data is not just transmitted at a single frequency, but occupies a range of frequencies about a central frequency, at which the signal is strongest. If the signals on neighbouring frequencies overlap, as shown on the screen, then there is a potential for crosstalk. OFDM ensures that there is no interference between adjacent signals, even when the signals overlap. This is because the minimum power of each signal occurs at the same frequency as the maximum power of those adjacent. This is what is meant by saying that the adjacent frequencies are orthogonal. As crosstalk is minimized, there is less need to retransmit corrupted data, allowing faster data transmission speeds. In the 2.4 GHz band, OFDM uses 4 channels, each of which is divided into 7 orthogonal sub-channels, which overlap but do not interfere with each other. A WLAN will use one channel and transmit data across all 7 sub-channels simultaneously. Finally, we're looking at MIMO, which stands for Multiple Input, Multiple Output. All of the systems described so far can use the wireless network adapters with a single antenna for sending and receiving signals. There are some referred to as SISO, which stands for Single Input, Single Output devices. MIMO is a technique used to enhance OFDM transmissions by using multiple antennas to transmit and receive signals. This increases the overall speed of data transmission. So let's move on to collision avoidance. So as you've already seen, some WLAN devices cannot detect collisions because they cannot listen while transmitting. So therefore they have to use carrier sense multiple access with collision avoidance scheme. This also has to deal with another problem caused by short range of WLAN networks, which is the hidden node problem. 2 WLAN nodes may be within range of the access point but not within range of each other, as shown on the screen. So we cannot rely on any direct communication between the 2 stations to prevent collisions. When a WLAN station wishes to send a frame to another station via the access point, it goes through the following steps. 1. Listen to the channel to determine if it's idle. If the channel is busy, back off and try again later. 2. Wait for a specified time. Then, if the channel is still idle, send an RTS, or request to send, frame to the receiver. indicating how long the data transmission will be, in order to reserve the channel for the transmission of the data frame. Number 3. Wait for a specified time for the receiver to send a CTS, means clear to send, frame, confirming the reservation. This frame tells all other nodes not to transmit during the reserved interval, also known as the network allocator vector. 4. Send the data frame, then wait a specified time for the receiver to send an ACK, or acknowledgement frame. So as you can see, the process is much more involved than CSMA/CD used by Ethernet. Each transmission of data frame involves waiting for a number of timeout periods, as well as sending these 3 control frames, RTS, CTS and ACK. As a result, the process is less efficient than collision detection. Although collision avoidance is designed to prevent collisions, it is not guaranteed to do so. For example, if a node fails to pick up a CTS frame, perhaps owing to local interference, it may start to transmit the same time as another node. When collisions do occur, the effect is the same as when interference damages a frame. The data is lost and will need to be resent. All of these factors mean that in practice, the data transmission speed achieved by WLAN will be less than the theoretical maximum quoted. And you'll notice that in a day-to-day, the speed is never as quick. So for example, if you have a 20 meg ADSL line and you're connected via wireless, you'll never get that 20 meg over Wi-Fi. So moving on to the speed of WLAN. The maximum speed of transmission in WLAN depends on the protocol being used. Currently there are 3 main WLAN standards in use, with maximum speeds varying from 11 megabits to 300 megabits per second. You will learn more about WLAN standards in the following section that I'm about to speak about. The actual speeds achieved are lower and depend on a number of factors. So we've got interference. You've already seen that interference will often result in frames being lost and having to be resent. Common sources of interference include other WLANs operating in the same or adjacent channels, cordless phones and microwave ovens. Then you've got range. The distance between end stations and access point will also affect speed. The further a station away, the further a computer or laptop is away from the access point, the weaker the signal. Subsequently, the weaker the signal, the more likely it is that it will suffer from interference from other radio sources. Then we've got to combat with physical environment. The presence of walls between a station and the access point will reduce the range of the signal. Large metal objects such as filing cabinets and lockers will tend to reflect signals. This can effectively shield the WLAN device from receiving a signal. The fact that metal objects reflect signals also means that a station might receive a signal directly from the access point, as well as receiving a reflection of the same signal slightly later. This also has the effect of degrading the quality of the signal. And then finally we've got different protocols. So the newer, faster protocols are generally backwardly compatible with earlier, slower ones. Allowing newer equipment to interoperate with existing installations makes it easier to migrate to new standards. However, in these cases, the speed of the transmission will fall back to that of the slowest equipment. So with all this in mind, how do you maximize the transmission speed? Well, effectively, when you're positioning your equipment, you need to bear in mind some of the following things. Place the access point in such a way as to minimize the distance to the furthest station. We've also, where possible, ensure that there is a line of sight between access point and each station. Avoid placing stations close to large metal objects such as filing cabinets, especially where the metal object is directly between the station and the access point. When operating in a mixed protocol environment, upgrade all of the equipment to use the same faster protocol as soon as practical. Carry out a site survey to detect other wireless channels in use by neighbouring WLANs and the places where those signals are stronger and more likely to cause interference. Most wireless access points use omnidirectional aerials, which radiate signals equally strong in all directions. If you find dead spots where the signal is weak, you should consider using directional aerials, which are capable of beaming signals in a particular direction. It may be necessary to install more than one access point, for instance where the area to be covered extends beyond the range of the wireless access point signal. To prevent signals being easily accessible outside the premises, you might also consider placing wireless access points away from the periphery of the site. However, this will not guarantee the signals cannot be intercepted outside the premises. So we'll move on to WLAN standards. So the main bodies influencing WLAN standards are shown on the screen. They include national and international agencies as well as professional and trade organisations. I'll leave that there on the screen for you to go through. The IEEE 802.11 standards. This suite defines WLAN standards. The features of the main standards currently in use are listed on the screen right now. Note 802.11g has a maximum speed of 54 megabits per second using OFDM, but supports DSSS for compatibility with 802.11b at the lower speed of 11 megabits per second. The maximum number of non-overlapping channels is shown in brackets. 802.11n has 4 non-overlapping channels, each containing 7 subchannels. The typical indoor range in meters. The actual effective range will depend on the number of walls and other obstacles between devices, as well as the presence of sources of radio interference. The original WLAN standard, now no longer used, was IEEE 802.11. This had a maximum speed of 1 megabits per second using FSSS and 2 megabits per second using DSSS. Although IEEE 802.11a is still in use, it was not widely deployed as it was more expensive to implement than the alternative 802.11b, and its high frequency signal did not pass so easily through walls and other obstacles. So, as we have already mentioned, it may be possible to operate devices using different standards within the same WLAN, or at below the maximum speed of the slower standard. On the screen you can see which protocols can be used together in a WLAN. Earlier you saw that it was possible to implement an ad hoc mode WLAN with direct connections between 2 or more stations without the use of an access point, as shown on screen now. The set of services provided by this type of WLAN is known as an Independent Basic Service Set, or IBSS. Ad hoc WLANs are not widely used, except as temporary connections between stations. Most WLANs are infrastructure WLANs, where stations connect to an access point which acts as a hub, relaying frames between the stations, like so. The set of services provided by this type of WLAN, where there is one access point, is known as a Basic Service Set, or BSS. It is usual for an infrastructure WLAN to be connected to a wired network, typically via a switch, as shown. This is not essential though. By using more than one access point, you can extend the range of a WLAN, as shown on the screen now. The set of services provided by this type of WLAN, where there is more than one access point, is known as an Extended Service Set, or ESS. The region within the range of an access point is known as a radio cell. Stations such as PC2, as you see on the screen, in 2 overlapping radio cells can connect to the access point with the strongest signal. In this case, data can be exchanged between PC1 and PC3 even though they are not within the same radio cell. As well as increasing coverage, an ESS WLAN can achieve greater data throughput by having overlapping radio cells which use different non-overlapping channels. On the screen now, The access points 1 and 2 use non-overlapping DSS channels 1 and 6 respectively in the 2.4 GHz band. PC1 and 2, which are in both radio cells, are fitted with cards that can establish links to both access points. Using the two non-overlapping channels, because the channels do not overlap, there is no interference between the two sets of signals. The features of WLAN modes and their associated service sets are summarised in the table on the screen. So moving on, cabling and connectors. Wireless LANs are implemented by wireless LAN network adapters, which usually communicate with wireless LAN access points connected to the cable Ethernet infrastructure. WLAN access points are usually connected to the wired LAN infrastructure using UTP Ethernet cable. Here is an example of some access points. You may find two other LAN technologies in use too, although they have been largely superseded by the newer, faster Ethernet standards. So you have token ring. In common with all broadcast technologies, token ring faces the problem of how to handle stations that want to transmit at the same time as each other. This is known as contention, and Ethernet handles this by allowing stations to transmit whenever the cable is quiet. Collisions can still occur, and these are handled by retransmission. Token ring, on the other hand, avoids collisions by using a form of CSMA, or collision avoidance. A special frame called the token travels around the ring, passing through each station in turn. Any station which needs to transmit first must capture the token. As there is only one token on the ring, only one station can transmit at any given time. After the station has sent its frame onto the ring, it releases the token to continue its progress around the ring, making it available for capture by other stations. Token ring runs at speed of 4 megabits per second, also known as slow token ring, and it goes up to 16 megabits per second, known as fast token ring. Some of the newer Ethernet switches also support token ring frames at speeds of 100 megabits per second. Another LAN technology is called FDDI, or Fiber Distributed Data Interface. FDDI specifies 100 megabits per second token passing dual ring LAN using fibre-optic cabling. It is similar in many ways to token ring. FDDI was frequently used as a network backbone. The Fiber Distributed Data Interface standard was defined by the ANSI X3T9.5 Standards Committee in the mid-1980s. The American National Standards Institute submitted FDDI to ISO, which created an international version of FDDI, completely compatible with the ANSI version. So, there we have it. We have completed Module 3. A lot to cover there. So, just a quick review. Once completed this module, you should be able to describe the basic operation of Ethernet, identify common Ethernet standards and their associated cabling and connectors, describe the basic operation of WLANs, identify common wireless LAN standards. So thank you for watching Module 3. Module 4 will be arriving shortly, and that is more about wide area networks. It's when we move on to Module 5, which is all about networking and TCP/IP, is where things really hot up and get interesting. So thanks for watching, and yeah, any questions or comments, please leave on my channel. Thank you. Bye bye.